Really happy to introduce Dan Ellis, who has historically been an influence on me when I was deciding what to do back in the late 1900s. Dan's work he was the first person I had seen try to do separation of arbitrary sounds, arbitrary mixtures of things, and it was really inspiring. And he has also become famous for his work in event detection and classification, and he's never been afraid to handle really tough problems. And one thing I really like about Dan is very unafraid to say when they're not working, and talk about their downsides, and yet still keep on going on these things. Yeah, without further ado, he's going to now talk about it's kind of a combination of separation and event detection. So take it away, Dan.
Thank you, John, for the introduction. That was very nice. Moving right along here. This is a talk I gave earlier this year at ICML, the audio workshop, which some of the organizers are here. And so, if it sounds familiar, that's why. This is and there's a paper for this, which is now on archive, currently under review. This work is a project. So, like John said, here in the sound understanding group at Google, we've been looking at. We did a lot of work on sound event recognition, and then a couple of years ago, we started thinking about sort of the whole end-to-end smart, intelligent sound processing, which is separation and then generation. And so we had this idea for a sort of what was then seemed like a novel idea for recomposing sound, for taking sound scenes and allowing you to manipulate them to modify them. And so we started this project about 2 years ago, and at that point, it seemed very novel. Since then, a lot has changed, and so some of this work you may feel is a little bit like, it's not as startling as it was then, but hopefully there's still some interesting things we can draw from this. I think the paradigm is still very interesting, and there's lots of more work still to be done. Okay, so there's a lot of people involved in this work, as is typical with industrial research. This is basically a sound understanding team, so thanks to everyone here. I was trying to work on these slides, and so somebody in the room said, "Why don't we try asking Gemini what to do with this?" So it's like, because there's like on this Google Slides interface, there's a little Gemini button. So like, okay, whatever. And so I said, "Can you improve the slide?" So this is what Gemini made for us. It made us these cartoons, which I don't know, pretty interesting. It managed to have intuited somehow Kevin's interest in running. Got some interesting people here, but it's also managed to expand the team somewhat, including Barrera, who I've yet to meet, but I'm looking forward to that. Okay, so what's the context here? The broad area is machine learning for audio. Okay, this was the slide I used at the Vancouver workshop. In audio, right, oftentimes when people say audio, they immediately think of speech, and a lot of times they're used synonymously. Beyond that, people say, wait, that's not the only kind of audio. There's also music, which is really important. And so we've seen a lot of work in that area in the past year or so. I have a background in that, but doing particularly with machine learning. But this is mostly about environmental sounds, like non-speech, non-music, the kinds of things that actually constitute most of the sounds that we end up listening to. I've always been interested in environmental sounds. They typically don't get a lot of attention, and so it's a nice place to investigate. Okay, so that's the domain. The different kinds of applications we can do. Like I say, a lot of my work has been in classification, or more broadly, understanding of sounds, analyzing the sound to try and figure out what the high-level abstract content is. More recently, we've seen all kinds of work in generation of content, including audio. And but like I said, this work is trying to go a little bit beyond that to do this idea of modifying sound. So you have a real-world sound recording, but you want to be able to change it. You don't want to completely regenerate it. You don't want to just say, it's not text to audio or whatever. You've got the audio as the condition. You just want to tweak it, and so that's the angle. When I gave this talk in Vancouver, I realized I was the only speaker in the session who didn't have an LLM in their model. No LLM here, but obviously there are plenty of places where we can insert that kind of processing to make it work better. Okay, so to introduce the actual model, I have a brief video which was prepared by Pascal, which it moves quickly, but it'll give us a good idea. So let's just watch that for a second.
This is a screen recording of the refreshed Recompositron demo. There's a sneeze in this audio recording. We will remove the sneeze using Recompositron.
Pregnant pause.
The sneeze has been removed. Unlike masking-based methods, there are no holes in the spectrogram. Or instead, we can enhance the sneeze. Multiple enhanced sneezes are generated. We can page through them and listen to them. We can also create new sounds. This will add dog, cat, and bird sounds. Again, we get multiple generations.
All right. I've seen that video a few times, as you can imagine. But it moves so fast that actually I'm still seeing new things. It's really great. But this is like the constraints of working in industry. You have to try and get your message across in 90 seconds. Otherwise, no one's going to know what you did. All right. Now, you get the idea, right? That we've got a recording. It's got some elements in it, and we want to be able to modify those elements somehow. This kind of scenario is something that we've seen in other systems, but typically the classic way of doing this is to condition on a straight text description. So it's like, here's my input, please remove the bird song, it generates the output. This seems like not a great match to the audio domain. Often, particularly if you're trying to deal with people who are used to regular editing tools, it's like, I don't want to have to tell you with words what I mean. I know what I mean. I want that thing right there. And so the idea was, can we actually have an interface more like that? And so this brings us to the idea of the event role. So we have this representation of the mixed sound in terms of something that looks a bit like a digital audio workstation or something. We've got a bunch of individual rows corresponding to individual perceived sound events, and then we can directly manipulate what happens to those. Now, so we have these labels down the side of the actual individual events, and then the things that we can do, we have actions that we can perform on these events. And the interface, or the system we've built, supports three kinds of actions. We can remove, we can delete, we can enhance, we can try and boost the amplitude of existing sound, or we can insert, create a new sound of a particular class. Now, obviously, this interface is, I think, pretty nice, but it does depend on having this transcription of the original sound mixture, the sound scene. This work doesn't deal with that. In fact, full disclosure, the examples I'm going to show you, the transcriptions are all manually generated, right? We have this AudioSet strong data set of clips like this with the sound events marked. Of course, in principle, we could use one of our sound event classifiers to generate this. This is exactly the output that the classifiers are meant to produce. However, if for the purposes of this project, we didn't want to further expose ourselves to the noise introduced by the inaccuracies in the classifier. We have built it, but it works better when we use the ground truth as input. So that's what we're generating. But in general, of course, you need to have something. If you're going to be able to edit arbitrary sounds, you need to be able to generate this for the sound for your input sound. in principle, I don't see that as a major obstacle because the systems we have that can do this work pretty well and can be perfected, I think. And then I think once you've got that, this is really the interface that you want, assuming that that works well. This is the interface you want to be able to edit your sound scene. Okay, so of the three actions I mentioned, deletion, enhancement, and insertion, enhancement is kind of the novel one. We've seen deletion before, we've seen insertion before. That's just generating arbitrary new sound events. But enhancement is kind of a little bit interesting because it combines both the idea of separating out, picking out what you can from the sound event that you're indicating, and also some generation, because sometimes there's, if it's a quiet sound event, you're not going to be able to fully extract it, so you're going to have to invent some extra detail to be able to make a higher amplitude version of that sound. So that's kind of a nice way of combining a couple of technologies that we have. Now, if we're going to provide for this, we can say, well, how do we actually specify? How do we indicate how enhancement, what we want to do? And there are a few options here. Ultimately, what you really want is to be able to say, here's this thing, and here's how I want it to be. I want it to be at this arbitrary output level, some specified output level. For the purposes of this model, we didn't want to have to get into generating or providing the interface for that. So we decided to give a fixed enhancement, just a 1-bit. You either enhance or you don't enhance. Even within that, we have choices, right? So we could say, okay, whenever I say enhance something, add some fixed level of gain to it, like 10 dB. Or we can say, when we enhance, I want a particular level of output. I want it to be at 15 dB absolute relative to the average background, something like that. That's what we went for, so that regardless of the input level, the output is always at the same target level. And that sort of made it nicer because then at least you can always hear them, and it's, the output is sort of the same regardless of how well the system identifies the input level. It doesn't have to accurately estimate the input level to know what output level it should use. But in general, this is something for a real system you'd want to provide more flexibility, give the user the control over that. Okay, so here is the sketch of the overall model. On the input side, we have the input audio, and we have the instructions here, the commands and the activity role, the points at which those commands are supposed to apply. The instructions here compose both the action and the target sound event. They're obviously, they're combined. And in fact, the way this system works is that this text is just treated as a string and is encoded wholesale using a fixed text encoder into an embedding. And then what we do is we multiply these together, and I'll talk more about that in the next slide. But we end up with a fixed size conditioning matrix. We then stack that with embedding of the audio using SoundStream. And then those vectors, which are now a set of time synchronous embedding vectors, are passed to the encoder, which then generates a set of outputs, also time synchronous. And then we have this reconstruction here. So this is a straight up encoder. This is now the autoregressive model where we go through and reconstruct a series of output tokens in response to the conditioning that we got from the input. And we're using a depth transformer here, which I think is probably something many of you are familiar with. So rather than just trying to predict a single level of tokens for the audio, we have a base level, and then we predict down from there to get levels of detail. So it's an RVQ, residual vector quantizing system, to give us better accuracy. This is not particularly part of the work. It's just this was the best synthesizer AR generation system we had to hand. There's a reference here to that idea of hierarchical reconstruction. Okay, so I want to talk a little bit more about this part over here, the way that we represent this edit conditioning. So I already talked about how the text has both the action and the target in there. And so this is like what we end up coming out of this sentence T5 encoder is a series of columns of embeddings in 1024 dimensions. I forget how many dimensions it is, some 768 dimension embedding of the text command. And then we have this activity role, which is the thing that we were drawing on in the interface, which gives us the time frames over which each individual row of this command should apply. And so we just use a matrix multiplier here to get this output matrix, which is now this set of time frames, but at the relevant time frame for a particular edit, we see a particular set of, a particular point in the embedding space indicating the edit. And of course, this is coming from a frozen general purpose text embedding. So there's nothing, the system has to figure out what those things mean, right? There's no shortcut. But we train it with examples so that it can figure out, okay, well that particular embedding corresponds to deleting this particular kind of sound class. The nice thing about this, because what happens is essentially if there are overlapping commands, they get added together. And so there's kind of this, you don't have to decide how many commands. You can add as many commands as you want because they're all going to get projected or combined into the same command space in the end, which works out nicely. All right, so that sounds great, but as I said, well, how's the system going to figure out what to do? And this is about how we're going to train it with the data to show it what we want. So we use this paradigm of synthetic target data. So the idea here is like the general operation is we have a sound scene with a bunch of different events in it, and we're going to want to pick out just a few of them, maybe just one or two, to change them. And so we want to get training data where we have two versions of a sound scene where one particular element in the scene has been modified in some way. And so we have this idea of combining real-world background sounds with a separate recording of a target sound, which we can then mix in with some modification and then use different mixes to get our input and output training examples. Now, for the backgrounds, we used AudioSet, which is this collection of random clips from YouTube videos. So they're often pretty dense. They often have a lot of stuff going on. And we have labels for them, which could be did this big labeling exercise. So of the, whatever it is, 1.8 million AudioSet clips, we selected for clips that were reasonably complex. So they had more than two classes labeled in them, right? We know which classes are present, so we can choose the ones that are more complex because they have multiple scenes to begin with, multiple sources to begin with, or classes. And we also make sure they don't have any big silent gaps in them. So of the 10 seconds, we insisted that there was at least 9 seconds with sound marked. In order to do that, we had to use just the subset of AudioSet that's been labeled with time labels saying where each sound occurs, right? So that's actually only like maybe 5 or 10% of the total data. But that gives us also gives us the opportunity to use these ground truth annotations for our experiments. So we have these backgrounds which are dense and complex. We then want to add in a target event on top of that, but we want that to be an isolated sound as far as possible. We don't want multiple sounds present or a single thing present. So what we did, we used Freesound for that, this open user-generated content site. A lot of the examples in Freesound are individual, well-defined sound events, although the tagging is basically free text. There's a subset that there's the subset of the FSD50K, the free sound data set, which has been more carefully annotated. So those have high-quality labels. What we did was we chose a set of classes from AudioSet, a subset of like 40 or so classes, which were going to be things that are reasonably well time limited. So things like footsteps, dog bark, burping, whatever. And we used text matching to try and find clips in Freesound that ought to sound like they were going to contain those examples. We then took those examples and passed them into an AudioSet classifier, which gives us these time-varying classification scores. And the idea there, so this is a Freesound example for door. We were looking for door here. And here's the actual spectrogram, and you can see it's reasonably well isolated door knock sounds. But here's the output of the classifier. And the idea here is like, well, if we're looking for door, does this clip actually have high score for door? So is it not just the text matching, but is it actually the content looks like it has door? And it says, yes, here's plenty high scoring for door. And then, okay, where is that door sound? So then we did sort of an isolating, operation here to find the time range that actually has the door knock, and we refine that both by the scores and then by the energy envelope of the audio clip to try and get a fairly tight edit around that little sound instance of a door knock. So here we have, a little over a second's worth of audio, which is like this first set of knocks, and that gives us our event. And so for these, we actually limited the events we selected to be between 0.2 and 2 seconds long, and we ended up with like 16,000 examples here across the 40 classes. This combination of like 100,000 plus clips for backgrounds and 16,000 foreground examples, we can then mix together to generate a large number of training examples. Now, what kind of training examples are we going to use? Well, we're going to train this thing on, here's the input, here's the command that we want you to operate, and here's the expected output, right? So it's like we need these triples. So we need both input and desired output for each examples for each kind of command. There are 3 kinds of action command here: delete, insert, and enhance. And so it's what you expect, right? For delete, we use the input as the mixture of the background and the target, and the output is just the background. So it's like, oh, the target's disappeared, magic. Insert is the same but backwards, so we have just the background for input, and then we have the inserted event as output. Now remember that in the command is combined with this activity role, so the system knows where it's supposed to insert it because that's implicit in the conditioning. But but it still has to look at the actual audio to see what it's supposed to do with it. And then for enhance, we have the same as the output here, but for the input, we mix in the input, the desired event at the right spot, but at a lower level. So the system learns to just take the original sound but increase the amplitude. Okay. We were able to generate these training examples on the fly. We wanted to make the system a little bit flexible, so we generated up to 2 targets per example, and we selected the target could have any of the 3 actions or no action at all. So in fact, these were like maybe equally likely, so maybe 1 in 16 examples had no modification and no command. We also made sure there was no time overlap between the targets just to make things easy. We chose a particular level. The levels we set were in this sort of target to background ratio, so we calculate the average level of the background energy and then set the target amplitude to achieve a certain energy ratio compared to that. 10 dB, which we use with a little bit of roving, is loud enough that you can see what's going on. You can tell that it's happening, and particularly you can pick it up in metrics, but it's still not ridiculously loud, so that it sounds okay in context. And then for the quieter inputs, the inputs for enhancement, we set them at -6 dB TBR, which is quiet enough to be difficult, but still quite audible in most cases. Okay, so how are we going to measure the results? We have a couple of metrics. We're using the standard metrics from the literature. The first one is an energy-based metric, but it's a little generalized. So it's called multi-scale spectral distortion. Comes from this DDSP paper. But the basic idea is you take a spectrogram, in this case, a MEL spectrogram. I assume it's some kind of spectrogram. Yeah, it must be MEL spectrogram. You take it for the desired output and the model output. You just literally subtract them in the log magnitude domain. You end up with some kind of difference here, and then basically you sum all these differences, the abs of the difference over all the cells to give you some kind of total distortion number. The multi-scale spectral distortion, multi-scale part is that you do this at different spectrogram resolutions and add them all up, and you also do it for both log and linear and add those up. But in practice, a single time spectrogram resolution and the log domain tends to dominate. So this gives you the right intuition for what's going on. One thing I want to point out here is these are actual model out. This is a real system, right? So this is like trying to I don't even know. I guess it's trying to delete this particular sound event here, so that we see this. This is where the main differences are. But we see there's low-level difference across the rest of the signal. That's because we're going through this, SoundStream encoder, then token prediction, and then regeneration. There's inevitable distortion involved in that, right? It's an analysis synthesis system, and leads to these kind of low-level differences between the input and the output, regardless of even if you're trying to do identity. The problem with that is that these differences can be of the same scale as the actual differences trying to measure in the enhancements. However, you can't hear them. I assert you can't hear them. You don't notice that there's some edit over here, whereas you typically would notice when it's working that there is an edit here. So that was a problem we had when trying to measure the overall metrics. The way we dealt with that was by restricting the metrics or differentiating between the region where we expected the edit to occur and the rest of the track. So here's this example again. But remember, we know anyway where the system was asked to make the edit change. And so the nice thing about this particular framing is that because the distortion is the sum of the abs distortion in all the cells, we can also calculate distortion over different time ranges. So here we've differentiated between the edit region and the rest of the clip, and we can sum up the rest we can sum these things separately to give us different metrics for the modified and the unmodified regions to check to see, well, how well did we do where we're trying to change it versus what did we do to the rest of the clip. Okay. To understand what's going on with these metrics and with the modeling, we looked at the histograms across the entire eval set of the metrics. And this is kind of a slightly unusual thing to do. Normally you take the average or something like this, but we're interested in distribution to understand what we're doing. And it was quite revealing. So here we can look at the metrics for the desired output versus the model output and compare it to the desired output versus the unprocessed, so the baseline of not doing any kind of processing. And then we can also do what I did in the previous slide of looking at the numbers over the whole clip, over just the modified region or over the unmodified region. So here I'm plotting the whole clip, which is dominated by the background because typically the modified region is only a 1 second of 10 or something like this, and then comparing it to what happens if we average it just over the modified region. Now, we have 4 lines here. They're the 2 kinds of metric for the 2 conditions, whole and modified. And what we see is this huge, narrow distribution of metrics. This is the multiscale spectral distortion, or it's the log of this average distortion. And there's this huge peak, narrow peak. This is comparing the model output to the input over the whole clip. And what it's saying is there's a large distortion here in all cases, and it's fairly constant. And that's just the model, this little bit of background noise that I was saying, the distortion that occurs because of going through the processing loop from input to output. One of the things you can do is you can say, okay, well, I'm not going to compare it against the input. I'm going to compare it against the processed output, which then would be, 0, or would include the distortion in the model output as well. But to be fair, we're doing it here, looking at this for the model output, and we see it's dominated by this background noise. Now, the orange and red here are the difference between input and output for the unprocessed. And we see there's this distortion here that occurs. It doesn't vary depending on whether we're looking at the whole clip or the modified region only, because it's basically uniform, right? It's the same level of distortion regardless of where you are. So we have these overlapping curves. Okay, finally we get to the green line, which is the desired output versus the model only in the modified region. And here we see there's a shift to the left. We've reduced the distortion, and so this is finally the evidence that our model is working. So as you'll understand, in the later metrics, we're going to look at the average of the green hump compared to the average of the orange hump to show the improvement that we've got from our processing. Okay, that was multiscale spectral distortion. We also use this other measure, which is commonly used in literature, the classifier KL divergence. Compared to multiscale spectral distortion, which is looking at the spectrograms, this is looking at a classifier output. The idea here is, particularly for something like insertion, there's no way that the model can know which dog bark you're trying to get it to insert. All it's told is insert a dog bark. And so to give it a somewhat fair comparison, we say, okay, you didn't know which dog bark to insert, but you were supposed to insert a dog bark. So let's build a dog bark classifier. look at the output of that from the desired output, look at the output of that from the model output, and compare those two. And so here's the example, right? This is this is a deletion example, so it's kind of easy. But here's the input, here's the processed output, here's the classifier applied to the input, which has, I think this is a meow sound, which is nicely detected here. Here's the classified output, classifier applied to the output, where the meow sound has been effectively removed. And then here's the KL divergence. Again, this is a frame-wise metric, so for every frame, we take the KL divergence between these two different sets of classifier outputs, and that gives us a number here. And you can see that it's like in the region of edit, we've got different values. And I guess the two curves here must be model output versus input, and unprocessed output versus unprocessed output versus input. And so we see the whatever, it's larger for one or the other. Sorry, I'm blurring here. One thing I want to draw attention to is that here's the actual edit region, right, this red box here. But we see the actual, the classifier outputs extend beyond that. That's because the classifier has a time context window. And so in order to do this modified versus unmodified, we broaden the window here by the size of the classifier window. So again, outside of this region, they're identical. But within the region, we can limit where we expect to see the differences. OK. We do a bunch of analysis. One of the things that we're interested in is like, well, what is the domain where enhancement is really working? I said before, when we're trying to enhance something that's really, really quiet, we can't really tell anything about it, so we have to do generation. If we're trying to enhance something that's already pretty loud, there's no generation involved. We just have to do a little bit of source separation and then boost the part that we can identify. In between, there's a region where we're sort of doing a bit of both, a bit of extracting what we can and then generating to fill in the details. So we did these experiments where we varied the enhancement input target between -30 and 0 dB TBR. We're trying to enhance up to enhancing to plus 15 dB, so always boosting it up quite a lot. And this is like the MSD of the result, and the solid lines are in our modified region. So the dotted lines are in the unmodified region where we expect it to be unchanging, but this is like our residual noise floor. What we see here is using the model output does indeed improve reduce the distortion, right? Improves the match between the intended output and the actual output. But this is using the unprocessed input. So even if you don't process it and you try and measure the difference, well, as the signal to be enhanced gets louder, the difference to the output, the distortion goes down. But the processing still does better. So what we're interested in is the difference between these. How much better did we do by applying the processing? So it's the subtraction of those two lines. And that's what this curve is. It's like this gap between these lines. All that to say, here's this peak. So here's the point where it turns out from a mid-range enhancement level of about -15 dB TBR, we get the best performance due to the model. And that's where, where the model is able to best take advantage of its ability both to generate and to separate. And so that was just to try and get us a sense of what the best level to test to illustrate enhancement was. In the end, we ended up using something much further down here, right? So around -6 dB as input, just so it was more audible. But you can see that we get different results for different levels. OK, so this is the overall performance table from the paper. So basically, we break it up into modified, non-modified, target, and non-target. And we compare comparing the input against the output versus the model output against the desired output. And then we have the MSD and KLD metrics, and we have the three actions: delete, insert, enhance. These, tables are not easy to look at. I guess things to notice here. If we take the input and compare it to the output, in the unmodified region, it's got no distortion because it's just copying through. Whereas if we take the model, then we see these low levels of distortion, but they're constant across the different operations. But let me talk a little bit more about the ablation experiments we did when we'll look in details at those numbers as well. So just to remind you, we have these three kinds of actions: remove, create, enhance. And we have three kinds of information that we're using for conditioning. The timing, when those actions occur, the action itself, and then the class of the action that we want to apply it to. And so we can try ablating different parts of that conditioning to see how much it affects the model performance. And we did this originally, and it was like, oh, wow, it turns out it doesn't need very much of this conditioning, because it turns out that the way we were testing it, the way we were training it, the model was actually quite able to guess different parts of the operation from the data that we were showing it. So we ended up changing the data that we were using to include these decoys. What I mean by this is, if I have something like this, which is an input with one big, event in the middle of it, the model can probably look at that and say, oh, probably this is going to be a deletion example because there was some background, there was a single thing there. I'm going to guess that you want me to get rid of that. Well, that was, a little too straightforward. So instead, we would have these decoys where we'd say, well, no, we're always going to put a single strong event in the input, so you can't necessarily guess what the operation is going to be. So if we have insertion, we're going to put an event here, but it's just you meant to copy that through. The insertion is actually somewhere else, so we'll tell you in the timing information that in the command that you meant to insert. So you can't just look at the audio and know what to do. And so basically all the inputs had one big event in them, and the outputs were different depending on what the command was. Enhance wasn't quite that because we had to have one weak and one strong event, but it was still the best we could do. And again, on the training data, there were between 0 and 2 edits per clip, so we can't just look at one thing and then decide what's going to go on. But the evaluation only had one edit per clip. All right, so here's the table of the ablation results. This first set is the unmodified, unablated, and the rest are different ablations where we're removing one sum of timing, action, and class. So TAC is all three present, dash, dash, dash is all three removed, and these are different results. Let's look in these bars separately. So now the first block here is the results I showed you before. The pale bars are the background, so we see there's this constant 1.3 MSD units of distortion regardless of the operation. And then here is the distortion for the different operations. Insert, it does the worst because for MSD, where you're comparing the actual signals, insert has to make a guess of what you wanted, so it's not going to be a very good match. Enhance and delete do a little better. These dotted lines show the unprocessed input. So, this is delete. We've got a big improvement there. And enhance, we've got a small improvement, but still improvement. The insert is under here as well, so actually a little bit worse than insert. Okay, so that's that. That's that. Okay. Yeah. So now we see here are the remaining ablated conditions. What we see is when we remove the class information, so TA here, the insert gets worse because, not only did we not tell you what example to use, we didn't even tell you what class to use. We told you where to put it, but not what it was, and so you have to invent something. So it's even less like the original, but it doesn't really affect the enhance and delete. If we remove the action, so it's like this is what we want you to modify. This is where we want you to modify it, but we're not telling you what to do with it. It turns out that both insertion's kind of fine, and enhance and delete are a little bit worse. I guess that's because it's confusing the operation between. You can't always tell what to do. And then if we remove the timing, which are these two blocks over here, everything gets worse because basically it's like I want you to remove a dog bark, but I want you to insert a dog bark. We're not going to tell you where. You have to figure out where, and so you randomly insert it. And we see that even affects the off-target metrics because sometimes it's going to do the modification outside of the modified region, doesn't know where that is, and that's what it makes errors. We can also look at, that was for the MSD, for the KL divergence, the classifier-based measures. We see that for the unprocessed baseline, I don't know, some stuff here. It's it's the same kind of trend. The only thing to notice here is that insert, which was we specifically used this metric to try and make insert easier, because like, well, you don't know what it is, but you know what class it is. And we do see that indeed, when we remove the class information, the insert metrics, firstly, insert is below its improvement on baseline. And without class information, insert gets much worse. So that's what we expected. Okay, future work. Obviously, this is just a proof of concept. For a real application of this, we want to provide richer ability to control what we're doing to the modifications of these things. For instance, it'd be nice to be able to modify the properties of individual sound events more finely, like not only their overall loudness, but pitch, reverberation, other kinds of attributes. And then other kinds of audio generation. So at the moment, all it knows is like it learns a bunch of classes, like dog. It'll generate dog barks, but it would be nice to be able to have it learn to generate, angry dog or small dog or things like this. Of course, the problem with all this, as other people working in text to audio know, is getting the training data. So where do I find good examples of small dog barks that are labeled as small dog barks? And that's, a common problem for all this kinds of deep learning work. Other kinds of conditioning, obviously, this is a little bit weird, and it's just an audio-to-audio task. Typically, if you're editing something, very often you want it to go with an associated video. So you really want joint generation of audio and video, which is something that has been going on with the VO project within Google. Other things you can do are this interesting idea of sound transformation. I'm not going to have time to talk about this, but just here's the idea. We have this thing which will enhance. You say, here's some background sound. I want you to make it louder. And by the way, this is the class that I want to make. If you need to fill in details, here's the class that you should be filling in details for. Well, you can ask it to do that, but give it a different class from what the original sound is. And the idea is then the system will generate something which reflects the details that it can discern from the low-level example, but will enhance it to be more like some other class. And so you can get some kind of class transformation. To be honest, this isn't working great at the moment because it really treats enhancement very much like insertion, and we'll just say, I don't know what that is. I'm just going to put a generic dog bark in here. But with enough training data, we have the opportunity to train it to do something like this. Yes, okay. So in conclusion, we've shown this autoregressive system to edit scene details for real-world sounds, and particularly we've introduced the idea of the event role as this way of specifying time ranges for edits, which is much better matched to this particular domain, this particular problem. We studied the actual performance of the model with these ablations, which had some interesting revelation and didn't go into huge amounts of detail, but it showed that there are, firstly, each of the conditions, each of the information that we're providing are controlling the model, but they have different levels of degree. And then, we looked at some opportunities for future work. Okay, so I think that's it. Thank you. Any questions? Yeah.
Yeah, we have time for some questions.
Yeah. Thanks for your talk.
Yeah.
I'm wondering, because currently you are editing the poor sound events, I'm wondering, have you considered when there is human speech there, how's
Yes.
the performance?
Yeah, so, right, so the sound events I was talking about were like these environmental sound things. By far, the most important application for actual editing is when you do have speech soundtrack and you want to be able to modify that. But that's compared to is this a dog bark? Is it a big dog bark? The detail of representation for human speech is much more complex, and we didn't really want to get into that representation. Separately, that work has there's good work on that, right? Where it's this whole transcript editing, and so the vision here is maybe we can have a hybrid system, because we can also do a pretty good job of separating out the speech from the background, and then we can have one model, specialized model for editing speech, and then this is for editing the rest of the sound. So I think we haven't handled that, but it'll be okay.
Thank you. And another question is that you consider the enhancement here by separating a sound from other background.
Yeah.
And I'm also wondering, that's quite similar operation like to substitute a sound event to another. Actually, they are same operation, but you didn't present performance here. But maybe you already considered.
Yeah. I mean, that's sort of, I think it's basically subsumed. You know, that kind of substitution is subsumed by deletion and then insertion.
Yes.
And so, I mean, you know, some of these things, there are a bunch of questions like that. It's like, okay, well, do we really need this operation, or can we just build this out of a sequence operation? So, like, you know, we got these. I have these multiple edits. It's like, well, do we need the model to do multiple edits, or can we just like do one edit at a time and repeat it? I think it's. I mean, I think it's interesting to say. Well, and the other thing is like, well, what about? I'm talking about this thing which removes the sound, or you know, introduces in a single step. How about we just separate first, you know, if we could do that with universal separation, and then process separately and then remix? What is the virtue of doing this all in a single step? In a sense, it's an investigation to say, well, can you do this in a single step? This is really where I started with this. It's like, if we try and do this operation to remove things without changing the background, how well does that work? And it works fine. The model is very happy. You know, it implicitly understands that it's doing implicit source separation, right, to remove sounds. But we don't actually have to have that explicitly. It's like, why, you know, you don't want that in the end, so just do this whole thing at once. And similarly, if you're doing multiple edits, okay, you're doing less damage to the signal if you just have a single pass through the analysis synthesis system. And so for that kind of thing, we could easily have done that substitution. If we put that in as a separate operation with some kind of conditioning, it would just be a question of doing the training, making the training data. We did actually have, that was the original, originally we had that. It was the original project. You know, the opening slide here, you may have noticed, had this weird picture of these plastic animals. The original project was dog-to-cat transformation, when we were detecting dog barks and converting them to cat meows. So exactly what you said. But it turns out that that wasn't the thing that people wanted to do.
Thank you.
All right. Okay.
Hi, Dan. It's a very cool talk and great results. I'm wondering, two questions. First, can it run on a CPU in some reasonable time, or it requires a GPU to be computed? I'm asking because many Hollywood studios would love to use this technology, but they are often not connected to the cloud. Second question, if you're not penalizing the MSR outside of the command region, are you not caring about quality there, or are you kind of crossfading with the input signal?
No, okay. So the first question, you saw the demo video, and that was a real-time thing. It takes about 5 or 6 seconds to process this 10-second clip with the existing model. That's with some array of TPUs behind it. I think it's like a set of 4 TPUs. It will run on a CPU, but it's a lot slower. It's not going to run in real time. But you know, those are just engineering problems. You know, the principle is there. But yeah, I mean, I think a lot of this stuff. I mean, I think there's a huge amount of work being done to make all these kinds of, particularly, I mean, this is autoaggressive, so you have to do sampling. So it's pretty painful. But there are better there are alternatives which can maybe make it more flexible and more realistic. And so I don't see there's big problems. There's also, this thing is not incremental, right? It's block based. It's looking at the whole 10 seconds at once, which is like 10 seconds is not a realistic scenario. But again, making it into a more of a very arbitrary length or online kind of operation, there's no particular technical problem with that. The other question was about, like, well, don't you even care about the background regions? The idea, the training objective was trying to minimize, was trying to predict the correct token. So we had, it's like we have the input, we have the desired output, we tokenize the output, and then we get a predicted set of output tokens, audio tokens. And the error is, the error of predicting the right token or where it falls in distribution. And that doesn't differentiate between the on-target and off-target regions. It was trying to optimize for both. And in fact, what we saw was when we trained these things, the MSD would go down monotonically for as long as we wanted to train, but it wasn't actually getting any better at the edit. It was just improving removing that background noise, right? So the actual training objective got very focused on trying to reduce that residual background distortion. So it is trying to do it. Not doing a great job, but I mean, that's more of a question of the audio representation and things like that. But again, I think that those things are not the limiting factor for what we're trying to demonstrate.
Maybe we have time for just one more question.
Thank you for the great talk. Very interesting. So here,
Hi.
So we know that sound classes can be hierarchical. For
Yes.
example, I remember you have a slide where you have a cat meowing sound.
Yes.
And you have labels of a cat meowing, cat, domestic animal, animal.
Yeah.
So let's say if I want to remove the cat, but keep the domestic animal and animal, would the two like replace a cat with a dog?
It could do. So, I mean, this is so in the example where I was looking at the classifier outputs. This is typical audio set. It has this hierarchy, and the way it's labeled is like you got a cat meow, but the label hierarchy has animal, pet, cat, meow, and it's like you don't know which label you're going to get. And so the classifier will typically output this whole block of a blur of those. Now, this model isn't tied to that classifier, right? What all this model knows is like, you showed me an example where you removed this sound, and you had this text which was like remove cat, and you had the time range. And so the model doesn't, it's not, I mean, it turns out that the text we gave it were always from audio set labels, but that was not intrinsic to the model, and we could have trained it with some kind of, LLM rewriting to use different synonyms. And so the model just learns like some point in language space, which hopefully cat and feline are nearby and stuff like that, and meow. And I'll just say, oh, it's round about there, it's this kind of sound. And it learns this more general mapping between language and sound. And so then, if it's like, well, cat is like in a ball of language space that surrounds other, domestic animals, you could then say, okay, just some pet sound, but a different pet sound, then it'll draw some random from that locality. So the challenge there, or the problem is the model has to learn how to generalize between language and a class of sounds. But again, that's just a training data problem, that if we showed enough examples of different kinds of animal sounds that are appropriately labeled with, relevant words which the language model appropriately places in a particular locality in the embedding space, then it will be able to do that kind of substitution you're talking about.
Thank you.
Thank you.
Thanks a lot. Yeah.